Hello everyone, and welcome to the 8th part of this MOOC dedicated to hydrocracking. In the first two parts, the role of the hydrocracker was recalled and we spoke about the feed characteristics. The first steps of the process consisting in heating up the feed was described and we spoke about the chemical reactions and associated yields. Let's continue to talk about the process. Since the effluent is very hot, about 420 degrees C, it is logically used to heat the mixture feed plus hydrogen recycled gas. In a series of feed effluent heat exchangers, the reactor effluent is cooled down to about 190 degrees C. Again, we can perform a heat balance to calculate the amount of energy recovered between 420 and 190 degrees C. At 190 degrees C, we have about 40% of the total stream, which is in gas form, and about 60% in liquid form. At this stage, the unconverted VGO, diesel and kerosene have been condensed. Note that the recycled gas, LPG and gasoline remain in gas form at these operating conditions. At this stage, the total amount of energy recovered is about 54 gigacalories per hour, according to the heat balance presented here. Note that we can neglect the heat released during the condensation of the molecules because the latent heat of condensation is quite low compared to the high temperature difference between 420 and 190 degrees C, which leads to a significant sensible heat. Remember, we said that we needed 31 gigacalories per hour to increase the recycled gas mixture plus VGO up to the furnace inlet temperature. So we will have a little extra calories for other needs that we will detail later on. Once the mixture is typically cooled down to a temperature of 190 degrees C, wash water is injected. But why is that? It is recalled that in the gas phase of the reactor effluent there is a presence of H2S and ammonia due to the pretreatment of the VGO. And as soon as we typically go down to 50 to 80 degrees C, these two molecules will combine and will be deposited on the surface of the equipment and in the lines in the form of an NH4HS salt. This NH4HS salt can even completely plug the equipment. To avoid this plugging, water is injected that will solubilize ammonia and H2S and create a solution of aqueous NH4HS. The amount of wash water injected must be carefully adjusted to avoid the formation of salts and must also not lead to having a too high NH4HS concentration, which would create a corrosion phenomenon very feared in the profession. In addition, it is necessary to ensure that the water injected remains partly liquid once injected. Indeed, if this water were to be 100% vaporized, as soon as the temperature would drop in the downstream equipment, the first droplets of water that would condense would have a very high concentration in NH4HS, which would make this water extremely corrosive and would corrode the downstream equipment. The profession recommends a concentration of NH4HS of about 4 weight% maximum. Let's do a quick calculation. If we have 1000 ppm of nitrogen in the feed, we will produce about 190 kilograms per hour of ammonia. This ammonia will combine with its equivalent in moles in H2S to make 540 kilograms per hour of NH4HS salt. And if we want the water to be concentrated at 4 weight% maximum, we must logically inject about 14 tons per hour of water. It is checked here that 14 tons per hour of water at 60 degrees C mixed with the entire reactor effluent at 190 degrees C leads to a three-phase mixture of water plus liquid hydrocarbon phase plus gas phase at a temperature of about 160 degrees C. At this temperature, about 20% of the injected water remains in liquid form. Once this water is injected, everything is cooled in a final air cooler before separating the three phases: the gas phase, the converted hydrocarbon phase, and finally the aqueous phase of the injected washing water, which has concentrated in NH4HS. This aqueous phase is usually routed to a sour water stripper, where we will remove ammonia and dissolve the H2S. Then this water is usually routed to the water treatment or recycled. The gas phase, on the other end, is recycled to the reaction section with a recycled gas compressor. The gas can be optionally washed with an amine solution to remove the H2S and thus maximize the activity of the catalyst. Note that in our case, we do not consider anyone. Indeed, it was judged that in our case, the concentration of H2S in the recycled gas was acceptable. It is here estimated at about 1 volume%. And the gas is then recycled to ensure an amount of hydrogen in excess compared to what is consumed in the reactors. It is a hydrogen recycled gas as we spoke about in video number 4. And some of the hydrogen is used as quench to control the exothermicity of the reactions in the different reactors. We talked about this hydrogen in video number 7. The hydrocarbon phase will be treated in the separation section to split the products. Now that we have described the process, let's talk a little bit about the operating variables of the reaction section. See you very soon in the 9th part to talk about these operating variables. In the meantime, do not hesitate to test your knowledge by doing the quiz and subscribe to my YouTube channel. Refining is exciting. See you very soon. Bye bye!